Hello and welcome back. Section 4.3, we get to play with homogeneous linear equations with constant coefficients. So first we'll kind of go over the idea of the section, then we'll get into the details. So if we have, we'll start with just an ay prime plus by equals, they said homogeneous, so equals 0. And a and b are just some real numbers. A is non-zero. Otherwise we just have the boring by equals 0. That's just y equals 0, sort of the trivial solution. So if this is true, then y prime is some constant times y. K again is just some real number. Well, the only non-trivial function with this property is y equals e to the mx. So then y prime would be m e to the mx, so m is just some real number. Well, then by substitution in the original, I would have a times m e to the mx plus b times y is e to the mx equaling 0. I can do a little factoring of that. I can grab an e to the mx from both terms and say this is am plus b equals 0. So I have a multiplication problem ending in 0. One of those factors has to be 0, but e to the mx, as you know, is never 0. So then the only one that could be 0 is my am plus b that we can solve. We can do something similar if we have, let's say, something of the form of a quadratic or even a third or a fourth power. We'll just look at the second power and then we'll kind of move in to the method from there. So ay double prime plus by prime plus cy equals 0. So again, a similar setup, only we allowed a second derivative to take place. So y is e to the mx like before. Y prime would be m e to the mx. So let's see if you can figure out what y double prime would be. Pause it if you need to. Okay, hopefully you figured out m squared e to the m times x. So doing a little substitution, we would have a times m squared e to the mx plus b times m e to the mx plus c times e to the mx equaling 0. Again, we can do a little factoring. Grab an e to the mx from all three terms, leaving us with a times m squared plus b times m plus c equaling 0 like before. E to the mx can't be our 0, so we would solve the am squared plus bm plus c equaling 0 and go from there. These we refer to as being an auxiliary equation. Sort of built off of the original. But it does actually help us get to some solutions. for M1 not equal to M2, so real and distinct. Our general format y would be equal to C1 e to the M1x plus C2 e to the M2 times x. For M1 equal to M2, that basically means that when we were finding the zeros, we had x minus M1 by another x minus M1, since M1 and M2 are the same, equaling 0. So x squared minus 2M1x plus M1 squared is 0. Well, we know that one of the y's would have to be of the form e to the M1x. So in y2, we can follow along with what we learned earlier in chapter 4 then. So this would be y1 integral of e to the minus integral of b dx over y1 squared times dx. So here, e to the m1x integral of e to the minus integral of negative 2 m1 dx over e to the m1x squared dx. So e to the m1x integral of, you have e to the 2m1x over e to the 2m1x again dx. Those will drop. So this will give us xe to the m1x. So in other words, when we want that second one, if we have a double root, just keep going up by a degree of x. So then y would equal c1 e to the m1x plus c2x e to the m1x. And leave a little more room for the complex. So complex, we would have, of course, complex conjugates. So M1 would be of the form alpha plus beta I. M2 was of the form alpha minus beta I, since they're complex conjugates. I'll let you kind of just read through why we end up here. We use a little bit of the Euler's formula on this. I'll just show you the broad strokes. So we have C1 e to the alpha plus beta I times x plus C2 e to the alpha minus beta I times x. And one tool they use, e to the I theta, is worth cosine theta plus I sine theta. So this will eventually land us on y equals c1 e to the alpha x cosine beta x plus c2 e to the alpha x sine of beta x. We're not going to go through the nitty-gritty details on how they get rid of the I on there and kick it back into the real numbers. I'm just going to ask that you be able to put this formula to work as well. So this one, the complex one, I'm not going to ask you about proving it. Alright, so let's actually start solving some of these And on these, now we won't be just sort of handed one of the solutions and be asked to find the other one. This one, we actually are able to find our own solutions now. So we'll look at 2y double prime minus 7y prime plus 3y is 0. So again, we're going to assume y is e to the mx. So y prime is me to the mx. And y double prime is m squared e to the mx. So we have 2 m squared e to the mx minus 7 m e to the mx plus 3 e to the mx equals 0. Grab your e to the mx and we have 2m squared minus 7m plus 3 equals 0. So notice that what becomes our auxiliary equation, each m is just raised to the same power as the number of derivatives that we've taken on the y, 2, 1, and 0 respectively on this one. So our auxiliary equation that we would solve, 2m squared minus 7m plus 3 is 0, since we know e to the mx is non-zero. This one happens to be factorable over the integers. So let's see, we would need a minus 6 and a minus 1 there. So m is 1/2 or m is 3. So then our equations, our solutions would be of the form c sub 1 e to the half x plus c sub 2 e to the 3x. Okay, so our next one, look at y double prime minus 24y prime plus 144 times y is equal to 0. So we have m squared e to the mx minus 24 me to the mx plus 144 e to the mx is 0. Factor e to the mx as usual, and then m squared minus 24m plus 144 is worth 0. We know e to the mx is non-zero, so we just solve m squared minus 24m plus 144 is equal to 0. This is our, or call our auxiliary equation. So this is m minus 12 squared is 0, so m equals 12, but that is a repeated root. We have 2 solutions of 12. So y is e to the c1 e to the 12x plus c2x e to the 12x. If you're not sure where that comes from, go ahead and just apply what we did earlier in the chapter. If we know that y sub 1 is e to the 12x, then y sub 2 is e to the 12x. Integral of e to the negative 24x over e to the negative 24x times dx. Those drop, and there's our y2 is x e to the 12x power. My apologies, minus and negative would be plus on each of these, and downstairs the 12x squared power to power e multiply, which is how we get the 24x there. So integral of dx is just x e to the 12x. All right. Next, we'll try out y double prime plus 10y prime plus 34 times y is 0. So we have m squared e to the mx plus 10m e to the mx plus 34 e to the mx is 0. Grab our e to the mx, we have m squared plus 10m plus 34 is 0. So we solve our auxiliary equation, m squared plus 10m. This one's not factorable over the integers, so I'll move that 34 and just complete the square. So m plus 5 quantity squared is worth -9, so m plus 5 is plus or minus 3i. So m is -5 plus or minus 3i. So then following our formula, y is c1 e to the -5x cosine of 3x plus c2 e to the -5x sine of 3x. Okay, so that takes care of our complex. After that, really we just start trying out some third or fourth power or third or fourth derivatives. They follow the same kind of idea. Try to break them down into squares. So if we have y triple prime plus 10y double prime plus 31y prime plus 30 is 0. Our auxiliary equation for that will end up as m cubed plus 10m squared plus 31m plus 30 is 0. And here's where you remember fondly your college algebra days. Look for a rational solution of this polynomial. So p, all the factors of 30, q, all the factors of 1. So p over q will just be all the factors of 30, so plus or minus 1, 2, 3, 5, 6, 10, 15, and of course 30 itself. So a little trial and error, and we find out that m equals -2 does very nicely. That gives us a nice, neat, pretty 0 there. Some more fond memories from your college algebra days. A little synthetic division. So a 1, a 10, a 31, and a 30. Bring down your 1, multiply and add, multiply and add. So now we can say, okay, if m equals -2 was a 0, then m plus 2 was a factor, leaving the other factor as m squared plus 8m plus 15, remainder of 0, of course, since we knew that was a factor. We can break it down a little bit more. This one happens to also be factorable over the integers. So m equals -2, we already had that guy. M equals -3, m equals -5 are other possibilities. So then y is c1 e to the -2x plus c2 e to the -3x plus c3 e to the -5x. Now, you might have written it down in a different order. That's all right. The constants are arbitrary. Alright, so this next one I'm going to ask you to sort of attempt it on your own. Just kind of pause it and then attempt it on your own. Play it when you're done. So you're going to look at y triple prime plus 2y double prime plus 5y prime equals 0. See if you can find our solution to that, our general solution. Okay, welcome back. So our auxiliary equation for this guy would be m cubed plus 2m squared plus 5m is equal to 0. We can factor, of course, an m from that. So m equals 0 is one solution, or m squared plus 2m. This is not factorable over the integers, so I'll just move the 5 out of the way and complete the square. So m plus 1 quantity squared is -4. Square to both sides, so m plus 1 is plus or minus 2i. So m is -1 plus or minus 2i. So then our y is c1 e to the 0x plus c2 e to the -1x cosine of 2x. So here's our alpha, here's our bravo, beta, technically. Let's see, sub 3 e to the -1x sine of 2x. And on this one, we just have a little cleanup. E to the 0x is a 1, so then y is c1 plus c2 e to the -x cosine 2x plus c3 e to the -x sine of 2x. So that's our general solution to the differential equation. So in our last one, we just look at doing a particular solution. So we'll try out, what did I pick? 3y triple prime plus 2y double prime is 0 with the initial condition 0. Y of 0 is -1. Y prime of 0 is 0. And y double prime of 0 is 1. So our auxiliary equation will get us started here, since we just have constant coefficients and a homogeneous linear equation. So this would be 3m cubed plus 2m squared is 0. So I can factor in m squared, leaving me a 3m plus 2, also equaling 0. So we have m equals 0. M equals 0 again, since this was a double root. M equals -2/3. So y1 is e to the 0x. So that is a 1. So then y2 would be 1 times x, or just x. y3 e to -2/3 of x. So put that all together on the next page so we know. We have then y equals c1. 1 times c1 is just c1, plus c2 times x, plus c3 times e to the -2/3 of x. And we just plug in what we know. So, well, let's do our derivatives as well. Y prime be c2 minus 2/3 of c3 e to the -2/3 of x. And y double prime then would be 4/9 c3 e to the -2/3 x. The information they gave us, they told us that y of 0 was -1. They told us that y prime of 0 was 0. And they told us y double prime of 0 was 1. Notice that the y double prime, we're down to just an unknown of c3. So that one I would actually start at the bottom and work our way up. So then 1 is equal to 4/9 times c3 times e to the -2/3 times 0. So e to the 0 power is a 1, so 1 is 4/9 of c3, so c3 is 9/4. And then we can just work our way back up the chain. So into the middle line then, using y prime of 0 is 0, we have 0 is worth c2 minus 2/3 of, now we know c3 to be 9/4 e to the negative 2/3 of 0. E to the negative 2/3 of 0 is still just a 1. That's sort of making a coefficient of 1. We can just knock it out then. So 0 is c2 minus, and let's see, we've got a 2 downstairs and a 3 upstairs, so c2 is 3/2. And then we move up the line again. So y of 0 is -1, so then -1 is worth, we don't know c1's value yet. c2 we know to be 3/2. Our x value, however, is a 0. c3 we know to be 9/4 e to the negative 2/3 times, there's our 0 again, making this whole thing a 1 there, times 9/4. So -1 is worth c1 plus 0 plus 9/4. So -4/4 minus 9/4 is c1, so c1 is then -13/4. So then our particular solution would be y equals c1 -13/4 plus c2 times x, so plus 3/2 of x, plus c3 e to the negative 2/3 of x, so plus 9/4 e to the negative 2/3 of x. So you should be able to convince yourself that that does work in the original differential equation of 3y triple prime plus 2y double prime equals 0. And it will hold then all three of these other properties as well. So in 4-3, I would recommend 1 to 39 on the odds, 49 to 57 also on the odds. If you have any questions, please come see me. Otherwise, I will see you next time. And please stay safe out there.